Hi, folks. My name is Vitaly Bragilevsky. I work as a developer advocate at JetBrains. And I'm here to talk about JetBrains. And in fact, there was a discussion maybe 3 or 4 weeks ago on Twitter about qualities that we would expect from a software developer. And some folks were talking about like professional means being right on time to deliver what they should deliver. And there was not an issue for professional software developer to be somehow attached to a product they were doing, to feel strong about this product, to care about it. And then I said, well, I agree that you have to check your time, you have to think like not to work more than you should, but this being attached to a product is actually important. And then someone answered, well, it's easy to say things like that if you work at JetBrains. And I thought, well, maybe because of that I work at JetBrains. So it's a good job when it's easy to care about products you are doing. So in this lecture, in this talk, I will try to say something about that. So we do enjoy solving challenging problems at JetBrains, and solving problems is really something that can be very captivating. So that's what we do. And this is my personal choice. So we are a very big company. We have more than 2,000 employees. And in this talk, I will tell you something about JetBrains itself. It will be a short overview. And then I've chosen 3 problems. Various folks work at JetBrains with these problems, not me. I'm just telling others about those problems. But I consider them interesting. It was fun for me to prepare this talk because it was fun to learn something about those problems. And of course, it won't be some deep discussion of those problems. I have only like 10 minutes about each one of them. But I think they're really interesting. And inside JetBrains, we have a lot of internal information about those problems, about approaches, how folks are trying to solve those problems. And like if one comes to JetBrains at some point, then it will be possible to learn all those internal materials. So not everything is available outside. So I will just show you something about that. All right, so what is JetBrains? JetBrains is a big company with a lot of products. Like this is our history, like about 16 million users. And plenty of products we work on at JetBrains. And so this is a timeline. It starts at 2000, year 2000, and year 2001, it's IntelliJ IDEA. In fact, before that, we had a tool which is called Renamer. That was the first refactoring tool that was produced by folks who became JetBrains a little bit later. And so they started with renaming things, and now we have dozens of products. And you see that there are years where we have many products released. There are years when we have not that many. And we are doing constantly, like every year we do something new, because we feel that there are problems with tooling. So if you look at our product catalog, you will see that we're doing IDEs for various programming languages, like our flagship IDE, IntelliJ IDEA, but we also have PyCharm, CLion for C and C++, PHP Storm. We have IDEs for database development, for example, DataGrip. We have IDE for Go programming language, Golang. We're also doing a lot of products for .NET ecosystem, like ReSharper for C# programming language, ReSharper C++ for Visual Studio. So there are also so-called plugins and solutions, something which is not about developing a product directly, but something which helps to do that. For example, Code with Me. Code with Me is a solution, is a plugin which is compatible with all our IDEs, which allows you to work in a team. Like you have one person here, another person there, remotely. They can communicate with each other. They can discuss code. They can do pair programming. They can teach and learn something together. So this is an example of a solution. Like there is a problem. We are all remote these days. So we can solve that with this particular solution. And then there are also team tools, tools which helps organizing work in a team, like Space. You can always see like when this particular employee has a vacation, so you don't have to like ping him because he's having rest at this moment. Or like we have Team City, which is a continuous integration tool. We have UTrack with tickets, with an ability to this morning I've got a notification from UTrack that, well, you have a lecture this evening, so are you sure you're ready to deliver that? So, and of course, I use many of those products every day. We also do programming languages, and we know a lot about programming languages. Kotlin is our main programming language, but besides that, we also do like MPS. MPS is a very powerful tool for creating domain-specific programming languages. Like it is very complicated, but there are folks who do research about our tools, about MPS. And of course, we have educational products. JetBrains was always very strong in this direction. And JetBrains Academy is well, it's hard to say what is JetBrains Academy, but it's everything related to education at JetBrains. And we have many products there too. We are also very close to the community, because for us, doing something for developers means doing something with developers in mind. So we have to talk to developers. We have to ask them, what do they actually need? Otherwise, it would be useless to provide something which they don't need. So for example, 1.7 million licenses were given to students and faculty members so that they can use professional tools. We support a lot of user groups out there. Some of them are Kotlin user groups, but not all of them. Like we can do same things with other programming languages, with other programming language communities as well. And we also support open source projects, and many schools and universities all over the world use our classroom license, so they can use our tools right in their classrooms. We have a lot of offices all over the world. So we have offices in the United States, in Europe, in Germany, Netherlands, Serbia, Cyprus. We have offices in Cyprus, apparently. We are in Cyprus here. Armenia. We also have an office in China. But if you look at the actual places where people work for JetBrains, you would immediately realize that it is really the whole world. Like my team, the team of developer advocates, we have folks in South Africa, for example. We have several folks in the United Kingdom. We have folks in Belgium, in Spain, in Taiwan. So many countries, and this is really what we are. We are multinational corporation, really. We have more than 2,000 employees at this moment, but we are hiring constantly, so we are getting bigger and bigger every day, I think. So we are really big company, but what we are actually good at, we are good at solving challenging problems. So as I said in this talk, I'm going to tell you about several interesting problems. And one of them is indexing. Of course, we're talking about indexing code. So our idea is to provide something which helps you to search over the code bases. And if you have a big project, like there is a statistics that says that like 70% of working with the code is reading it. And if you have millions of files in your project, then you need to read those millions and you have to search over them. So you never know where this particular class is defined, so you have to search somehow. And well, of course, we have tools for doing exactly that. So I'll start with this particular example, find in files. Like here I have opened an IntelliJ IDEA project, which is quite a big one, not the biggest. There are much bigger projects in this world, but it is quite a big one. And if we try to search something using find in files tool, we get results immediately. I just write some word, and then I have like a lot of matches in a lot of files, and this is really quick. So the question is, how is it possible? Well, it is possible because of this procedure of building indices. Like we have code base, but we should build indexes not only about code base, but also all the dependencies. Because when you write something, some code, you never write from scratch. You have a lot of dependencies. You have standard library. You have dozens or hundreds of libraries besides standard library. And you have to be able to look for code in those dependencies too. And then in professional projects, of course, you have a lot of build system files, like Gradle or make files, whatever. And you also have to index them too, because you have to know where this particular binary is described, so what should be put in there. So you have a lot of sources to build your indices, and then you run some procedure, and as a result, you get indices. Many of them, actually. If you are interested in the theory of building indices, there is this great book, Introduction to Information Retrieval. And when I was talking to folks who actually do indices at JetBrains, they said, well, we've just implemented everything from chapter 4 and chapter 5. And then they said, well, of course, we've changed something because we are doing better than in that book, and it is very old. I think it's 2008 or something. But this is the base. And I'm not going to talk about base here. You can read for yourself. You can just access it over internet freely. What is inside those indices? Well, there is basic procedure. There is so-called trigrams. And with trigrams, we build basic indices over text. So what is trigrams? If you have a word, you can split it into sequences of 3 letters, like JetBrains is Jet, ETB, TBR. So, and then you build compute hashes over every trigram. And this is the basic part of any text index. With that in mind, you can build direct index, and direct is not very useful. So if you have a file ID, then you can, using that direct index, you can compute hashes from this file. So you know everything which is inside this file. But the most interesting part is inverted indices. Inverted index means you have you're looking for some trigram, and then you can find a set of files where you can find this trigram. So this is actually search. So whenever you search something, some text in your project, every word or regular expression is actually split into trigrams, and then we look at the set of files which contain all those trigrams, and then we get this list of files, and then you can look at them. There is a list of files, and you can look if is it what you need or maybe not. For example, if we are talking about IntelliJ IDEA, we have 1.5 million source files, and the size of the index is 500 megabytes. Well, with relatively, like with my laptop, to build those 500 megabyte index takes like 5 minutes. When we are talking to our customers, building indices for them sometimes takes up to 40, maybe 50 minutes. So this is a little bit problematic for them. So when you open a project for the first time and you don't have any indexes in that project, well, sometimes you need to wait. But once you have all those indexes built, everything works at the speed of light. Like really, you can check for yourself. But for me, working with these text indexes is not very interesting, actually. So this is very well-known algorithm for building this stuff, and it's also only about searching over text. But we are programmers, and well, sometimes we look for text, but in many cases we are interested in something much more sophisticated. So, for example, in this screenshot you can see search over usages. So we have some interface. It doesn't matter what we actually have there. So we have some interface which is called entity, and we look for usages of that interface. And also very quickly we can get a result. Like there are more than, well, here is more than 500 results, usages in all places in this project. And we know that this interface is used as a class or object property type in 13 results. Sometimes it is an extension receiver type. So it is used as a super type in 280 cases. So that means that this is a base of some hierarchy of interfaces of classes. So you can get this information very quickly. But apparently, text search isn't very helpful here, because there can be much more occasions of this word entity in the code base. So we are looking for something much more specific than text index. Well, really, we have many other indexes as well. So text and. So for example, for this find usages action, we have so-called ID index. So for every file, we run a lexer. Lexer is a component, software component, which looks for words in the file. And we extract from all those words, we extract identifiers, IDs. So we take filter out all keywords like private, public, class. We're not interested in that. So we're looking for IDs. And from those IDs, we build specific ID index. And with that specific index, we can look for usages. So yet another index. Then there is also go to implementations command. Like we have that entity, and we want to see where this interface was implemented. Well, yet another index, declaration index. We parse files, so it's next step. So it's not just only about reading IDs, reading words, but it's actually trying to figure out the structure of that file. Like this is a class. This class contains several methods. It's not full-blown programming language parser because, well, we want to be fast at this stage. We don't want to compile the code. So we have simplified parser, which builds so-called declaration trees, well, like really modules, classes, methods in those classes. And from those trees, we build yet another index, like with declarations. And we have dozens of different indices inside all this stuff. And we can build them differently, but of course, it all takes time. But once we have all those indexes, we can do a lot of things very quickly. So many other indexes are also there. So for example, here you can see this, this is the result of search over all instances. Like entity, not instances, maybe implementations. So we have here more than 900 implementations of this interface. Direct implementations and indirect too. So very quickly, because of that job that was done before that. we have many programming languages, and it turns out that indexes very heavily depend on language. Like sometimes, well, if it's text search, then it doesn't matter. But if it's a programming language, then we have to parse it somehow. And then some languages, it takes much longer to build those indices. Like when I was talking to a guy who is doing that, he said, well, for example, there is a Java. And for Java, building indices is just like a breeze, very quickly. Very simple programming language. And for them, hardest programming language in terms of indices was TypeScript. TypeScript is very complicated if you want to build indices for that, like 10 times slower. And well, of course, we have to think about that. And if we are building IDE for a particular programming language, then we have to think about trade-offs. What do we want? Whether we want to have longer indexing stage, and we want to get larger indices, and then our search will be very smart, or we can save time on the indexing and don't provide those smart capabilities for actually doing indexation, doing search. So, well, they do their own choices. For example, in IntelliJ IDEA, there is a rule. There should be a linear dependency between time of indexing and the number of files. Like twice more files, twice longer indexing stage. And this is done because all indices are additive. So you just parse a file, index it, parse another file, index it. So you can stop at any moment. And at this moment, if you index like half of your code base, you can work with that half, and you know nothing about another half. In other IDEs, for example, in Selenium, it's not like that. Like Selenium needs to parse many files to build one index. That's because of some problems with C++ programming language. We all know there are a lot of problems with C++. This is just one example of that well, thing. Like we have WebStorm, we have PHP Storm, and every IDE like that should think, what should they do for this particular programming language? And then, of course, we have to think about a lot of different stuff. Like, for example, right now, indexes are built concurrently. But the problem is that if we have more than 10 cores, and well, right now we have like 30, even in laptops, then scaling of that concurrently built is a bit problematic. So this is something our folks work at this very moment. They think how to re-implement building those indexes to reuse all available computational power. And this includes like re-evaluating algorithms, inventing some new algorithms, thinking about how to keep those indices. So a lot of problems, but this is something that they're doing right now. One of the problems is that when you have an index, you work with your IDE, then you close it, and then you open it again, and then sometimes IDEA starts to re-indexing everything. Well, sometimes this happens. So this is a big problem, and right now we have a lot of things going on, how to prevent that re-indexing, how to understand why this re-indexing was actually happened at this moment. There are a lot of diagnostics about that. But this is really a problem we are trying to solve. For example, here in this direction, like we never work with files from the hard drive because it takes a lot of time. Like we have virtual file system, like in memory. And when someone says, well, IDEA use a lot of memory, well, that's for you. That's because we need to keep a lot of information in memory and not to try to access hard drive every second, right? But then there is file watcher, which looks at the hard drive, and then it reports some changes to that virtual system. And there is a special stage, which is called scanning. We scan over the virtual file system and try to realize if there was something changed or not. So, and if there was a change, then we have to reload it from hard disk and then re-index it, stuff like that. We also tried to use version control system information. Like if your project is under Git, then you may immediately ask Git, well, what was changed in the last time? And then Git provides you with a lot of information about that, and you use that to re-index to make the time smaller, right? We also use a lot of information in memory. Like if there was a crash in IDE, if you just very quickly turned off your computer, then all those in-memory indices just gone, and then you have to rebuild them. But we don't want to save everything every second because, well, it takes time. So it is possible to get corrupted indices, because indices, well, they are databases. And as usual with databases, everything can be corrupted. So we have to deal somehow with that. There are shared indices, like for very well-known dependencies, like for JVM, standard library, there are shared indices. And you can download them. And then there is always this trade-off. You can either download them or build them. And you never know which is faster, actually. And in many cases, it's faster to build because, well, remember, 1 gigabytes or 500 megabytes, that's quite a lot. So it takes time to download that. So, but we do support that stuff. And then every computer is different. Like file paths are different here and there. But you have this one shared index for some dependency, and then you have to deal somehow with the specifics of this particular computer. So you download it, and then you have to think how to connect it to your particular file system. This is also a problem. So we have not much time left. Problem number 2. Totally different. But once again, I've chosen these 3 problems because they are interesting and they are very different, and they shows you the whole range of things we are doing at JetBrains. So now I'm going to talk about static code analysis, which has a very, very long history at JetBrains. So what we are talking about here? Just some piece of code in Kotlin. Do you see something in this code? We have a lot of developers here. Are there any problems? We have some variable, and then there is a while loop, and then some condition, and then we do something. So if we write this particular code in IDE, then you will immediately see that this condition is always false. So IDEA knows somehow, no matter the while loop, well, it knows like it was 0 in the very beginning, and then at every iteration we do +2. So this will be 2, 4, 6, so this I will be always even number. So that's why the result of I and 1 is always 0, and the condition is always false. And of course, this is a synthetic example. So you never write code like that, of course, unless you write code like that, because we all know that programmers do stupid things all the time, right? So there is one, well, almost real-life example with very similar problem. Do you know this children cartoon fixes? It's Russian one, but there is English translation. It is very, very popular, very nice. And in one of the episodes of that cartoon, there was this professor, he's called Professor Chudakov, and he's building a manipulator, some arm which is managed by the program. So he built this tool, and then he wrote a program that managed this manipulator, and then manipulator just gone wild. He tried to attack the professor himself, his friends, so a lot of problems. And then professor realized that there was a problem in the code, and they actually show this code. So in this code, like there is a person identification, and then so this is some screen from laptop from that professor, and you see that there is a conjunction of two conditions. If this person is not Chudakov and it is not like Fixiki, like those his friends, then manipulate a lock. In this program, in this code, we have a logical problem. So it actually says, like, lock this manipulator, prevent it from doing anything if it's anyone except for Chudakov and Fixiki. And if it's Chudakov or Fixiki, then just do something about them. So this professor looks at this code, says, oh, I know what's the problem here. And then he just edits this code and changes it to this one. And said, now everything will be all right. I don't know what IDE is used here by this Professor Chudakov, maybe like VS Code or something, I don't know. But it's definitely not IntelliJ IDE. Why? What's the problem here? Right. This condition is always true. The problem before was logical error, which was impossible to fix with IDE. But this one now, and he says that it's all right at this time, but it's not, because this condition is always true. And how IDEA knows that? Well, for example, we have the code like this if condition with this disjunction. What we actually do, we build some intermediate representation, which is a stack-based programming language, some internal programming language inside IntelliJ-based products. Like we do push, put it on the stack, then compare with other values. We just some like intermediate representation, some simplified view of that code. And then we interpret that with so-called abstract interpretation. And we realize that at the moment when we reach second part of disjunction, this value should be Chudakov. And that means that it cannot be Fixiki at this point. So, well, we use those facts and we show the inspection shows that, well, there is a problem in this code. So you like developers should do something about that. Well, this is technically called data flow analysis, which is based on abstract interpretation. So we interpret this program, but in most cases some part of it, usually some function or a method. And we use some very specific types, not just regular programming types, but types with an information about actual values, which in theory can be there. And then we deduce some facts out of that. Like there, we look, well, let's try this Chudakov. If it's not Chudakov, then do something. So there are some algorithms behind that, of course. We do that online. So whenever you type anything in your method, there is this algorithm abstract interpretation which is running behind it at this very moment. There is also some interprocedural analysis, which is something between methods. But mainly it's something about one method. We don't know anything about it outside. What is going on outside? We're not interested. But we know that there is a problem right here. This code, this static analysis, first appeared in Java. And one of the interesting characteristics of our company is that our current CEO, Chief Executive Officer, Max Shafirov, wrote it. So, well, there are some traces of that code in the current implementation of that algorithm. And the most interesting thing is that this analysis is not tied to one programming language. Well, there are parts of that analysis which are tied to programming language, but many other parts can be used for any other programming language as well. For example, right now, there are 4 languages for which we can reuse all that stuff. Like, technically, the only part which can be different is the first part when you build intermediate representation, right? Everything else doesn't depend on any programming language. So we have this fine algorithm there, and we can reuse it, so we can enjoy the results. Where can we use that stuff? It's not only about providing our inspections, like this specific information about our value, our conditions, or stuff like that. But of course, we can report those. There are many warnings in IntelliJ IDE and other IDEs which tell you that there is something wrong. But actually, we can help other inspections too. Like any offer of inspection, like some piece of code which checks something in your code, they can reuse that analysis. They can run it, and then they can provide you with an additional insights. This can help to reduce so-called false positives, like inspection, which says something, but is actually it's not the case. So we can reduce those using this analysis. We can use it for code completion. Like in many cases, if you know exactly the value of a variable, you can know something about its type. For example, if in Java you use something like instance of. So you know type specifically, you can use this information to provide more precise code completion. Like these methods, but not those methods. We now get a lot of additional information about expressions. Like there is an expression. Usually, well, it is some integer value. But with this analysis, you can get something like, well, this is an integer value, which is greater than 0, but smaller than 100. So this is something very expressive type. So it's like, well, if you know, like from type theory, there are many specific type theories for specific types. So here's something which resembles that stuff. Like more complex information about value of this particular variable. We can also use it in debuggers. Of course, what does it mean to debug something? When you stop at breakpoint, you have some information about values. And if you run data flow analysis with this particular information, then you can get some insights. For example, here in this slide, there is some function. We've stopped at breakpoint, and we know the value of one variable. And this information allows us to see that from 3 different parts of conditional expression, only the first one is actual. So we don't have to consider anything else. We just know that it will be the first one. So we grayed out every other piece of code here. So this is runtime, of course, because we are doing debugging. But we've run this static analysis at this point. And now we know much more about this program. So we can be sure that it will be the first case and not everything else. Static analysis, problem number 2. Problem number 3. Sometimes we design IDEs from scratch. So nothing about indices, nothing about code analysis. We would design an IDE. And here I'm talking about Fleet, our new IDE, new attempt to design a program, to design an IDE for software developers. Just several examples how we can use that. So here I have set up with a virtual machine. I have a server, like this white one is a Mac OS, and then another client, which is on Windows, this black one. And I can connect client to a server. So this is something we can do. This is an example of remote development. We can make it a little bit more complicated. Like, there is a server, which is really server. Space development environment is a specific system, so you can run your server in the cloud, and then you can connect to that cloud from several clients from different operating systems. And then you can like forward ports, so you have one ports declared on one machine, but you can access it from another machine as if it is a local, something local. How is it possible? Well, if we are talking about Fleet, we've started with an architecture. With this architecture, we have a workspace, which is a central part, and then we have several front ends or clients which connect to the workspace. We have several file systems, maybe on different computers, and they're all connected to the same workspace. And then we also have backends. Backends here provide information about specific programming languages. So Fleet itself knows nothing about Kotlin or C++ or C#, but we have those backends which know everything about programming language. They provide everything, including indexing, static analysis, whatever. So this is an example of an architecture. Okay, but it turns out that we can do a lot of things with this architecture. For example, we may have a single desktop computer, and everything works at this computer, like every component. We can also have something totally different. Like we have a server, and we have a front end. We have two computers at this scheme. So we have a front end, and it has its own file system, of course, like local settings can be saved there. And we have a server with workspace, with backends. And this is a setup when you have a not very powerful laptop, but you have a powerful server, and you can run everything which requires, like, I don't know, like 64 gigabytes of memory. Everything is there. You can run all your very demanding in terms of memory and power tools on the server. But we can also have something like this. One server, many front ends, like many folks working with the same workspace at the same time. And the idea behind Fleet was to implement something like that. If you looked at the book on distributed systems, like any book actually, like there is a book of Tannenbaum, for example, distributed systems, and many others. Every single book has chapters on these topics. There is a chapter on architecture, like centralized, decentralized, hybrid architectures, a lot of them. How those systems manage themselves, self-management, like we have a lot of components, we have to put this component there, put that component there. There is a chapter on that. There is something about processes. You run some part of the program at this computer, some part of the program at that computer. Sometimes you have to migrate your code, like to send code, not just data, but to send code to another machine. There is also a chapter on communication. Then you have services in that distributed system. You have to access those services. You have to give them names. There is a chapter on that. And then you have state here and there, and you have to synchronize it. And then there is a problem of consistency. You should replicate your data so to access it quickly. You have to think about fault tolerance. What if one component just was broken? What about others? Will they continue to work? You have to think about security. So every book on distributed system actually has these chapters. And the most important parts of those books are something about services, synchronization, consistency, and replication. And the nice thing is that this is actually the core of Fleet. When we were designing Fleet, we were thinking about program in a distributed setting. And that's why we have to implement these parts from the very beginning. So Fleet at its heart is a distributed system, and in fact it is a distributed database. So we call it rhizome-DB. If you Google this word rhizome, you will see that it's some plant with many roots, and you never know what is root and what is not, but it is really distributed. Every piece of state is presented with entities. Do you remember that interface entity which I was showing you before? It was exactly this code, so entity is at its heart. And there were like more than 600 implementations. So there are many entities. Everything is presented with entities. If we read some state, and what is programming? We read some state, and in this case, that means that we are looking up the database. If we change state, that means that we are running a transaction against that database. Just as in usual database, like MySQL, Postgres, whatever. We have some data, and we run transactions over that data. So this IDE is actually a distributed database. Like really, like if you open a file, this results in some transaction. If you edit code, this will be a transaction. Because, well, you edit code at this part, at this computer, but everything that you've changed here should be delivered to another front end in another computer. So, and then if you do something at the same time from different computers, you have to work with those transactions. So something should end up in the database, something should not, because there may be some problems in that. So everything is a transaction, and the whole work of Fleet is actually this running time. We have snapshots of the database, and you write to the database, run those transactions, and you go from one snapshot to another snapshot. And it's a distributed system. You're never able to access information like immediately. So you may read some older snapshot at this point, but then it will be updated. So we have to look carefully about this sequence of operations. No one writes SQL apparently. Everything is done via compiler plugins. So this is an example of entity. You have an interface with some variables in there, and everything is transformed into something inside that database. So for example, you can, like, this is an example of a transaction, for example. So you just say this last seen UTC. So you should say, well, this is a transaction, changing value in a database. Well, just this was copied from the source code. There are many technical intricacies inside there. Like, for example, every state, every entity is represented with those triples. Like we have entity ID, we have some attribute and value. And if we change something in that database, we remove old values and put new value there, like deletion and insertion, like usual operations in the database. We should record everything that was changed in a transaction, because you have some, like, remember, you have front end. So if something was changed, then you have to reflect this change immediately. So you should know what exactly was changed. And if this part of display was changed at this time, like this part of code at line number 146, then you have to change this particular line and not everything else. You don't have to rewrite everything, because you know what was changed precisely. And then we have to track history of values, because, well, we need to validate transactions. If you have several players in this game, they can work together, but they can do that at the same time. So you have to check what was earlier. So you have to track history. And everything, of course, is done there. One example of how this actually works. Like, this is a diagram for code completion. And the main idea of that is that there is a so-called completion service discovery. You may have many completion services depending on the programming language. Like for Rust, it's just one mechanism. For C# is another. For Java, the third one. So you have to choose somehow. Well, if you draw those diagrams, they look very sophisticated. But technically, what's going on actually inside that? There is no service discovery. The only thing that we have, like looking up the database, because everything is inside that database. Like technically, we have some entity with some attribute, we just look it up, and as a result, we get the implementation of that service, because everything is inside that database. If you are interested in these things about Fleet, there is a Fleet Below Deck series in 6 parts. There will be more. Like right now, I'm working on the part of networking in Fleet. We're going to tell about things, how communication is implemented in Fleet. But here we're talking about distributed transactions, state management, a lot of stuff like that. So very complicated piece of software. And it's fun to develop it. And that's something that we do at JetBrains. So thank you very much. It was a very condensed talk. I think I'm almost in time. So yeah, if you have, that's it from me. So if you have any questions, please. Or maybe we can continue going to the pool. I don't know. Yeah, but thank you. So that's what we do. So if you enjoy solving challenging problems, you can maybe think about joining JetBrains and solve them too. Thank you. Yeah.